Right now, the most successful ideas in physics flatly disagree about how reality works. General relativity says the cosmos is a smooth, flexible space-time. Quantum mechanics says nature comes in sharp, grainy packets. Put them together and instead of harmony, we get collision. Tonight, in Why Do Two Great Theories Contradict Each Other? The battle between quantum and cosmic theory, we'll move slowly through that collision. From curved space-time around black holes to the jittering quantum fields beneath every atom. Step by step, we'll see why equations that guide GPS satellites and equations that guide particle accelerators refuse to live inside a single calm framework. You're invited to settle in, breathe a little deeper, and let this strange conflict unfold like a slow cosmic experiment. And with that, we open part 1. Why can't our two greatest theories fit into one single equation? Where the clash between quantum mechanics and general relativity first shows its full structure. The deepest frameworks of modern physics collapse into disagreement the moment we place them side by side, is less than #0. 5# is greater than general relativity reports, a universe built from smooth, continuous space-time. Quantum mechanics reports a universe built from abrupt, granular events. These descriptions are both confirmed by decades of observation, yet they refuse to merge, as if reality were holding two incompatible blueprints at once. The conflict becomes unavoidable whenever scientists attempt to describe places where gravity becomes extreme and distances shrink beyond what our instruments can comfortably resolve. When NASA mapped the motion of stars around Sagittarius A star using the Chandra X-ray Observatory and the Very Large Telescope, the predictions of general relativity matched every recorded orbit with astonishing accuracy. Saoyu Jinho, Lin, 5# is greater than. At the same time, when experiments at particle accelerators, such as Fermilab and CERN, probed distances smaller than a trillionth of a meter, every result matched the expectations of quantum field theory. Two theories, each flawless within its own domain, turn fragile when they are forced to operate together. The story reaches further back than the 20th century. When Albert Einstein presented general relativity in the 1910s, he described gravity not as a force, but as curvature, a geometric deformation of time and space produced by mass and energy. The theory predicted the bending of starlight, the shift of Mercury's orbit, and the delayed arrival of signals from distant pulsars, is less than #0. 5# is greater than more. Then a century later, the Event Horizon Telescope produced the first image of a black hole's shadow, matching Einstein's equations with precision, down to a few percent. Meanwhile, the quantum picture emerged from scattered breakthroughs. In the 1920s, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger revealed that atoms behave not like miniature solar systems, but like probability distributions, governed by quantized energy levels. Later physicists unified electricity, magnetism, and the weak nuclear force into a single quantum field framework. Every new collider result reinforced the same message. Nature at the smallest scales comes in discrete steps. These two pictures do not simply differ in tone, they contradict each other in structure. A geometrical field that curves continuously cannot at the same time behave like a quantum field, built from particles that exchange energy in sudden jumps. When theorists attempt to quantize the gravitational field, treating the geometry of spacetime like the electromagnetic field, the mathematical expressions gain uncontrolled infinities, is less than #0. 5# is greater than renormalization, a procedure that rescues other quantum theories, fails completely. Throughout the 1960s and 1970s, researchers attempted to resolve this tension by exploring conditions near gravitational collapse. In 1974, Stephen Hawking used quantum field theory surrounding a black hole's horizon to show that black holes emit thermal radiation. This prediction required quantum vacuum fluctuations and curved spacetime to interact, yet the deeper structure connecting them remained absent. Hawking once remarked that the universe doesn't allow perfection, and this discovery exemplified how progress often exposes new layers of conflict rather than resolving them. Observations continued to push these limits. ESA's Gaia mission measured stellar positions with micro-arcsecond accuracy, confirming subtle relativistic effects across tens of thousands of light-years. Yet the same data implied fluctuations too small for relativity alone to explain. Fluctuations better interpreted through quantum principles. The universe appeared to favor both pictures simultaneously, even as the theories resisted unification. The tension becomes clearer when we visualize the scales involved. General relativity excels at describing structures larger than a few kilometers, such as neutron stars, galactic cores, and the gravitational lensing measured by NASA's Hubble and JWST. Quantum mechanics excels at distances smaller than nanometers, where electrons tunnel and quarks bind through gluons. But at the Planck length, roughly 1.6 times 10 to the minus 35 is less than #0. 5# is greater than the very meaning of distance becomes uncertain. The notion of a smooth spacetime collapses. Any attempt to probe smaller scales requires energies so large that gravity itself becomes dominant. Physicists often compare this to trying to describe ocean waves with equations meant for individual water molecules. The description only works within its own range. Going beyond that range requires a new language. This is the realm where quantum gravity must appear. A theory capable of handling both the curvature of space and the discrete behavior of quantum fields. Many attempts have been proposed. In the late 1980s, loop quantum gravity suggested that area and volume come in quantized units, like pixels of geometry. In string theory, the building blocks of matter are vibrating strings whose tension creates particles and forces, including gravity. In the 1990s, the holographic principle proposed that the information inside a region of space could be stored on its boundary surface is less than #0. 5# is greater than a concept inspired by black hole entropy calculations by Jacob Bekenstein and Stephen Hawking. None of these ideas has yet produced a complete, experimentally confirmed unification. Still, each provides partial hints. For example, NASA's observations of gravitational waves from merging black holes reveal that strong gravity events exhibit extremely clean spacetime oscillations consistent with relativity, but leaving narrow windows for quantum corrections. Inférieur à 10⁻. 5# is greater than these corrections remain too small for our detectors, but their expected signatures guide new missions, such as LISA, planned by ESA and NASA for the early 2030s. Another angle appears when considering high-energy particle collisions. Experiments at the Large Hadron Collider have not identified any deviations from the standard model that would hint at quantum gravity particles. Yet theorists note that if gravity behaves differently from other fields, the signature might not resemble the expected spin-2 graviton. The conflict extends into cosmology. During the early universe, temperatures surpassed 10 to the power of 32 Kelvin, and densities exceeded anything reproducible on Earth. Under those conditions, quantum fluctuations shaped the seeds of galaxies. NASA's Wilkinson Microwave Anisotropy Probe and ESA's Planck satellite both mapped these fluctuations with extreme accuracy. Is less than #0. 5# is greater than. The patterns matched inflationary models, but revealed statistical features that might trace back to quantum gravitational physics beyond our existing frameworks. At the opposite extreme, black hole evaporation raises issues that neither theory can resolve alone. If a black hole evaporates completely, what happens to the information carried by the particles that fell inside? Quantum mechanics forbids information loss, but general relativity provides no mechanism that preserves it. The black hole information paradox undermines the completeness of both theories, is less than #0. 5# is greater than Leonard Susskind, one of its early investigators, described the paradox as a deep inconsistency in our understanding of nature. Historical progress often arose from confronting contradictions like this. In the 19th century, James Clerk Maxwell unified electricity and magnetism by recognizing that light is an electromagnetic wave. In the early 20th century, Einstein unified mass and energy through E equals mc², is less than #0. 5# is greater than. By analogy, the conflict between quantum mechanics and general relativity may represent the next frontier, demanding a deeper organizing principle that both theories approximate under different conditions. Multiple research programs now explore this frontier. Quantum simulations attempt to recreate gravitational effects in controlled laboratory setups using ultra-cold atoms or superconducting circuits. Observatories such as JWST search for early galaxies whose structures might reveal hints of quantum gravitational dynamics, is less than #0. 5# is greater than. Meanwhile, theoretical work continues to refine approaches such as asymptotic safety, causal dynamical triangulations, and emergent gravity models, each seeking internal consistency and empirical footing. Across all these efforts, one truth remains. The universe consistently supports both pictures, depending on the scale we examine. Relativity guides the arcs of planetary motion and the warping observed during gravitational lensing events. Quantum mechanics guides the energy levels measured inside atoms and the interference patterns observed across countless experiments. The contradiction lies not in the data, but in our current frameworks for interpreting it. Richard Feynman once remarked, "Nobody understands quantum mechanics." He did not mean it as a dismissal, but as an acknowledgement that our intuition, shaped by everyday experience, struggles to match the mathematics that governs the microscopic world. The same can be said of relativity. Its predictions are testable and reliable, yet its geometric interpretation of gravity stands apart from the particle-based description used everywhere else in physics. This unresolved tension is not a flaw in science, but a sign that our understanding is incomplete. Future measurements, perhaps from space-based interferometers, next-generation particle colliders, or improved black hole imaging techniques, will eventually reveal which path leads forward. Until then, these two monumental theories remain like parallel maps of the same landscape, accurate within their regions, contradictory where they overlap. And as these two frameworks continue to collide, a further layer waits beyond the horizon. A layer where the structure of space-time itself begins to break down, urging us toward part 2. How did Einstein turn gravity into geometry, while quantum physics turned forces into fields of particles? Gravity breaks apart from every other force the moment we examine it closely. Electromagnetism, the strong force and the weak force, behave as quantum fields made of particles. Gravity alone refuses this description because Einstein rebuilt it from the ground up and turned it into geometry. To understand why this split matters, we return to the early 1910s, when Einstein completed a 10-year effort to describe gravity in a way that matched astronomical observations far better than Newton's law. He realized that mass and energy do not simply pull objects, they reshape the structure through which objects move. The path of a falling stone or a circling planet is not dictated by an invisible force, but by the shape of space-time surrounding it. When Einstein published the field equations in 1915, he provided a framework capable of predicting phenomena no previous theory could explain, such as the shift in Mercury's orbit and the bending of starlight during eclipses. 4 years later, in 1919, astronomers measured that bending during a total solar eclipse. Photographs taken hours apart showed background stars shifted slightly from their usual positions, exactly matching Einstein's prediction. The confirmation reached newspapers worldwide. It demonstrated that space-time behaves like a deformable medium, able to stretch and curve under the influence of mass. The implications were immense. A planet moves the way a marble moves across a stretched sheet. The sheet is not merely a visual analogy, but an accurate reflection of how the geometry itself responds to energy. By the late 20th century, NASA and ESA would test general relativity further, using spacecraft and radio observations. Missions such as Gravity Probe B measured how Earth drags spacetime slightly as it rotates. Pulsar timing arrays recorded the subtle slowing of binary neutron stars as they radiated gravitational energy. Each observation strengthened the same conclusion. Gravity is a geometric phenomenon, not a particle-mediated interaction. Yet at the same moment, general relativity was gaining confirmation after confirmation. Another revolution was taking place at microscopic scales. Experiments in the early 1920s showed that electrons do not move smoothly. They jump between discrete energy states. Later, tests using particle beams, bubble chambers, and accelerators revealed that forces act through exchanges of particles. A beam of light is not a continuous wave, but a collection of photons. The strong force arises from gluons. Radioactivity involves W and Z bosons. This picture, known as quantum field theory, treats every force except gravity as a set of oscillating fields. When one field vibrates in a certain way, particles appear. When fields interact, particles exchange energy. Inside CERN's detectors tracks left by collisions reveal these processes frame by frame. Photons curve one way, muons another, and short-lived hadrons leave fragments before they decay. Quantum field theory describes nature in sudden increments. Einstein's geometry describes nature in smooth contours. Bringing them together is not simply a matter of placing two equations side by side. It is a matter of reconciling two incompatible views of what a force even is. During the 1950s, physicist John Wheeler summarized the relativity view in a sentence that condensed the theory into a simple structural rule. Space-time tells matter how to move. Matter tells space-time how to curve. His words describe a self-consistent feedback loop. The presence of mass determines the geometry, and the geometry determines the paths mass will follow. Nothing in Wheeler's framework involves particles carrying gravity. There is no mediator. There is only curvature. Quantum field theory, however, demands a mediator for all forces. The electromagnetic force involves photons. The strong force involves gluons. The weak force involves W and Z particles. When theorists attempt to give gravity a mediator, the result is a hypothetical spin, two-particle, called the graviton. But inserting such a particle into the equations of general relativity breaks the internal consistency of the geometry. The prediction of the graviton requires a flat background spacetime. Yet, relativity says spacetime is dynamic, never fixed. This mismatch prevents an exact translation between the two languages. The difference becomes clearer when we follow the story behind several key discoveries. In 1974, NASA's Uhuru satellite and later X-ray observatories identified sources so compact and massive that only black holes could explain them. At the same time, ground-based radio telescopes tracked pulsars orbiting one another with exquisite precision. Their orbits decayed at a rate predicted by general relativity, confirming Einstein's idea that gravitational waves carry energy away. 4 decades later, in 2015, the Laser Interferometer Gravitational Wave Observatory recorded the first direct detection of gravitational waves. The signal represented two black holes merging more than 1 billion years ago. The wave pattern matched Einstein's equations so precisely that model and data were nearly indistinguishable. The observation provided another confirmation that gravity behaves as curvature, not as particle exchange. Yet the moment we zoom inward, quantum behavior overwhelms geometric reasoning. Inside atoms, electrons occupy fixed energy levels. They jump between states by absorbing or emitting photons. Experiments using high-resolution spectroscopy and precision clocks have measured these transitions with extraordinary accuracy. The results agree with the predictions of quantum electrodynamics to more than 12 decimal places. This difference in precision highlights the split. Quantum theories achieve unmatched accuracy in small-scale phenomena. Relativity achieves unmatched accuracy in large-scale phenomena. Neither theory fails in its own domain, yet both fail where the other dominates. James Peebles, who studied the early universe using data from the cosmic microwave background, once noted that the entire large-scale structure of the cosmos arises from minuscule quantum fluctuations stretched by cosmic expansion. ESA's Planck satellite confirmed this by measuring temperature variations in the background radiation down to millionths of a degree. Those microscopic fluctuations were quantum in origin. Their large-scale consequences are governed by relativity. The two theories jointly shaped the universe's structure, yet the bridge linking them remains incomplete. Attempts to find that bridge grew over decades. Quantum field theory in curved spacetime extends the quantum picture slightly, allowing vacuum fluctuations near black holes to produce radiation as Hawking predicted. Observations from Chandra and XMM Newton have measured high-energy emissions consistent with extreme gravitational curvature, providing indirect support for these ideas, but the deeper unification still eludes us. The tension becomes more tangible when physicists attempt to quantize the metric itself. The metric is the mathematical description of spacetime's geometry. Quantizing it means treating the geometry like a vibrating field. But the moment this is attempted, the calculations generate divergences that cannot be removed. Unlike the electromagnetic field, whose infinities can be managed through renormalization, gravity produces an infinite number of corrections with no way to determine which are physical. This mathematical breakdown mirrors the conceptual breakdown between the smooth and discrete views of the universe. Historical details help reveal why the tension persists. During the 1970s, experiments at SLAC and Fermilab mapped the behavior of quarks inside protons and neutrons. These results showed that the strong force becomes weaker at short distances, a property called asymptotic freedom. Because the force simplifies as we probe smaller scales, the mathematics becomes easier, not harder. Gravity does the opposite. As distances shrink, gravitational effects grow stronger until the geometry itself becomes undefined. This divide leads directly to the Planck scale, where length contracts to around 10, raised to the minus 35 meters, and energy rises beyond anything humanity can currently achieve. At such scales, neither relativity nor quantum mechanics alone can describe events. Space-time curvature becomes dominated by quantum fluctuations, and the idea of a smooth geometric surface ceases to hold. This region represents the starting point for any future unification. NASA and ESA missions continue to supply data that challenge both theories. JWST images of early galaxies reveal structures forming faster than expected. Gravitational lensing measurements show curvature produced by dark matter, whose microscopic nature remains unknown. Satellite timing tests, using atomic clocks aboard GPS networks, demonstrate relativistic time dilation daily, while quantum corrections influence the accuracy of those same clocks. The world we inhabit operates within both frameworks simultaneously. Carl Sagan once reflected on the scientific process with the words, "We are a way for the cosmos to know itself." In this context, the tools we build reveal how sharply the universe splits along these theoretical lines. The cosmos presents a geometry that bends under mass. The microscopic world presents fields that vibrate in discrete amounts. Understanding why nature adopts two distinct descriptions is one of the central goals of 21st century physics. As the search continues, gravitational wave detectors will improve, particle colliders may reach higher energies, and telescopes will capture finer details of spacetime near event horizons. Each new measurement will bring the two pictures into sharper contrast, showing more clearly where the unifying principle must emerge. And from this growing contrast, a deeper frontier becomes visible, guiding us toward Part 3, where researchers confront the failure of quantizing a smooth spacetime and uncover the mathematical instabilities that reveal how incomplete our current tools still are. What breaks when we try to quantize a smooth spacetime? The first cracks appear the moment scientists attempt to treat gravity the same way they treat every other force. They take Einstein's smooth spacetime, add quantum fluctuations as they would in electromagnetism or the strong force, and expect the mathematics to settle into something manageable. Instead, the expressions surge uncontrollably. Every correction term produces another divergence, and the entire structure rises into infinities that no known method can remove. This difficulty did not emerge from speculation, but from decades of careful attempts. In the 1960s and 1970s, quantum field theory had already unified the electromagnetic and weak forces and provided a clear account of the strong force. Renormalization techniques allowed physicists to strip away infinities and extract meaningful predictions. The method worked because the underlying forces became simpler at smaller distances. With gravity, the opposite occurs. As the scale shrinks, the theory grows more complex. To see why, we return briefly to Einstein's geometric picture. In general relativity, spacetime acts as a dynamic structure. Mass tells it how to bend, and the bending determines the motion of mass. This reciprocal interaction works smoothly across astronomical distances. Observations by NASA's Hubble Space Telescope, ESA's Gaia mission, and gravitational wave detectors all confirm that relativity describes large-scale phenomena with exceptional accuracy. But when theorists treat the spacetime metric as a quantum field, they replace continuous geometry with a fluctuating surface. These fluctuations feed back into the curvature in ways that intensify the problem. One early attempt to quantize gravity involved expanding the metric into a background spacetime plus small perturbations. The idea was to treat the perturbations as quantum fields. This technique works in electromagnetism where fluctuations ride on top of a fixed background. But general relativity has no fixed background. Spacetime itself is dynamic, and the moment one tries to treat it as a field living on something else, the theory loses internal coherence. A second issue arises when physicists attempt to calculate loop corrections, which are a normal part of quantum field theory. In quantum electrodynamics, loop corrections adjust particle masses or charges in predictable ways. These corrections become small at high energies, which makes the theory manageable. For gravity, loop corrections never shrink. Instead, each new correction becomes larger than the one before. The result is a series that cannot converge, leaving no way to extract finite numbers. This is what physicists mean when they say quantum gravity is non-renormalizable. The consequences of this failure extend beyond the mathematics. If gravity cannot be quantized in the same way as other forces, it suggests that something deeper is happening at small scales. For instance, NASA's observations of neutron stars and black holes show that gravity becomes incredibly strong in compact regions. These environments test relativity under extreme curvature. When two neutron stars merged in 2017, producing gravitational waves detected by LIGO and Virgo, the signal contained information from a region where spacetime was pushed close to its limits. The waves matched Einstein's equations perfectly, but they also highlighted how far the theory must be stretched to describe the earliest moments after the collision. Experiments and observations at the opposite end of the scale also point toward the problem. Measurements of atomic energy levels, the magnetic moment of the electron and quantum interference patterns confirm quantum field theory to extraordinary precision. If gravity was simply another quantum field, its effects would appear at extremely small distances. Yet, after decades of particle collider experiments, no such effects have been detected. CERN's highest energy collisions probe distances far smaller than the size of a proton, and still, there is no sign of quantum gravitational forces acting like particle-mediated interactions. A key point in this story occurred when physicists developed quantum field theory on curved spacetime. Instead of trying to quantize gravity fully, they treated spacetime as a classical background influenced by quantum fields. This approach allowed Stephen Hawking to predict radiation from black holes in 1974. His calculation showed that quantum fluctuations near the event horizon should cause black holes to emit energy. Later studies using NASA's Chandra X-ray Observatory provided indirect evidence supporting aspects of Hawking's model. However, this method stops short of full unification. Quantum fields, living on curved spacetime, can describe processes near black holes, but they cannot explain what happens inside them. The singularity predicted at a black hole's center lies beyond the reach of both theories. Relativity predicts infinite curvature, while quantum physics predicts that spacetime should fluctuate violently before reaching such a point. These competing predictions create a boundary where the known laws of physics lose meaning. Stories from the early era of quantum gravity research reveal how scientists confronted these challenges. In the 1970s, Bryce DeWitt and colleagues attempted to express the gravitational field in a quantum wave equation. Their formulation, known as the Wheeler-DeWitt equation, removed the notion of time from the description entirely. While mathematically elegant, the resulting framework lacked a clear operational meaning. Even today, physicists debate how to interpret it. The attempt shows how profoundly different gravity is from other forces. When approached with quantum tools, gravity forces theorists to reconsider fundamental concepts. Another effort involved treating gravity as an effective field theory. This method does not try to make the theory renormalizable. Instead, it accepts that the theory works only up to a certain energy limit. At energies well below the Planck scale, physicists can extract predictions that match observations to high precision. Experiments using lunar laser-ranging satellite time measurements and GPS networks rely on these predictions every day. But as energies approach the Planck scale, the approximations break down, leaving open questions about the true nature of spacetime. ESA's Planck satellite has provided some of the most detailed information about the early universe. The temperature map of the cosmic microwave background reveals faint patterns that trace back to quantum fluctuations amplified during cosmic inflation. These patterns carry clues about physics, operating at extremely high energies. Yet even this data stops short of revealing the structure of spacetime at the smallest possible scales. The Planck mission measured the universe to extraordinary precision, but it could not peer into the quantum structure of spacetime. This limit is not a failure of technology. It is a fundamental boundary imposed by the theories themselves. To observe spacetime below the Planck length, an instrument would require energies so large that it would create a black hole instead of a measurement. In other words, gravity shields its deepest layers from direct observation. This self-shielding behavior is one reason physicists believe a new theoretical framework is necessary. Among these attempts, some insights have emerged. For example, theoretical studies show that if gravity had the same type of renormalization structure as electromagnetism, then quantum corrections would be measurable in high-energy cosmic ray events. But observations from detectors such as the Pierre Auger Observatory do not show these signatures. Similarly, if spacetime fluctuated in the way described by simple quantization schemes, then signals from distant quasars would show blurring effects. Observations from Hubble and JWST show no such blurring. The absence of these effects reinforces the idea that spacetime cannot be quantized like a normal field. John Wheeler once remarked, "Spacetime is telling matter how to move, and matter is telling space-time how to curve. His statement captures the essence of relativity, but also highlights the difficulty in merging it with quantum rules. In quantum mechanics, fields do not simply curve, they vibrate, superpose, and exchange energy through particle interactions. These behaviors resist any clean translation into geometry. As the search continues, physicists explore new methods that go beyond traditional quantization. Approaches such as causal dynamical triangulations and loop-based models treat spacetime as a collection of discrete building blocks. String-inspired frameworks treat particles as extended objects. Each proposal attempts to avoid the infinities that appear when gravity is quantized, like other fields. Observations from JWST may eventually offer new insights. By examining the earliest galaxies, JWST captures light that has traveled since the universe was a few 100 million years old. Subtle patterns in galaxy formation, lensing distortions, and early clustering behavior may reveal hints about how gravity operated under conditions where quantum effects were stronger. Scientists will spend years comparing this data with predictions from various quantum gravity models. As each new measurement narrows the gap, researchers approach a threshold where the mathematical instability of quantized spacetime must yield to a more complete description. The tools of the future, whether based on gravitational wave interferometers or high-energy particle experiments, will challenge both relativity and quantum mechanics in ways neither theory has yet faced. From these unresolved tensions at the Planck frontier, a more detailed mystery comes into view, carrying us naturally toward Part 4, where spacetime itself begins to fragment under extreme conditions and forces scientists to confront what may lie beneath the smooth surface we have always assumed. Does spacetime stay smooth forever, or does it shatter at the Planck scale? Spacetime begins to lose its familiar shape the moment we push nature to its smallest measurable distances. At scales approaching the Planck length, the smooth geometric surface, described by Einstein, no longer behaves as a continuous structure. Calculations suggest that spacetime becomes irregular, turbulent, and unpredictable, as if the very notion of distance breaks into discrete fragments. To understand how scientists arrived at this idea, we return to the Planck units first introduced at the beginning of the 20th century. These units are constructed by combining the speed of light with the gravitational constant and the quantum constant. When these values emerged, they define a regime where gravity, quantum mechanics, and relativity all exert comparable influence. The Planck length is roughly 1.6 times 10 to the minus 35 meters. It represents a scale so small that if you enlarged a proton until it spanned the observable universe, the Planck length would still be smaller than a grain of dust within it. No experiment has ever probed such a distance directly, yet theoretical indications point to this as the frontier where spacetime itself may change character. During the 1970s, physicist John Wheeler introduced the phrase quantum foam. Wheeler envisioned that at extremely small distances, fluctuations in spacetime caused by quantum uncertainty would become strong enough to distort geometry. Instead of a smooth landscape, the geometry might twist, ripple, or even momentarily form tiny wormholes and bubbles. Although this idea could not be tested directly, it emerged naturally from attempts to merge quantum rules with relativity. Research into black holes provided some of the strongest hints that something unusual happens at very small scales. When NASA and ESA observatories examined emissions from regions near black hole horizons, they confirmed that radiation behaves exactly as predicted when classical gravity bends spacetime. But models describing the center of a black hole produce a singularity, a point where curvature becomes infinite. In physics, infinities usually signal that a theory has reached a regime beyond its validity. Many researchers suspect that the singularity predicted by relativity is not a physical object, but an indication that spacetime must adopt a different structure at extremely small distances. The Big Bang presents a similar challenge. ESA's Planck mission mapped the cosmic microwave background with remarkable precision. These maps reveal temperature variations imprinted when the universe was only 380,000 years old. The data confirmed that early cosmic expansion behaved as predicted by inflationary models. Yet, when extrapolated back to the first fractions of a second, classical relativity again predicts a singularity. Just as with black holes, this suggests that the smooth spacetime of relativity may not apply in the earliest moments of the universe. Loop quantum gravity emerged as one attempt to address this problem. Beginning in the 1980s, researchers explored a framework where spacetime is not continuous but made from finite building blocks. In this picture, area and volume exist in quantized steps, similar to the way energy levels in an atom exist in discrete amounts. These building blocks are often described as loops, forming a network that defines geometry. Within this framework, singularities can disappear because distances cannot shrink indefinitely. Another major direction came from string theory. Instead of treating particles as points, string theory describes them as extremely small vibrating strands. Vibrations correspond to different particle types. Because strings possess size, they avoid the infinities encountered when point-like particles interact. String theory also predicts that spacetime may have more than the familiar 4 dimensions. Although these dimensions remain hidden at everyday scales, they could influence physics at the Planck length. Neither loop-based models nor string-based models have yet received direct experimental confirmation, but each provides insight into how spacetime might change at small scales. For instance, if spacetime consists of discrete units, there might be observable consequences for extremely high-energy cosmic rays. Some researchers examined the arrival times of gamma rays detected by NASA's Fermi telescope to search for patterns indicating that photons of different energies travel differently through a discrete spacetime. So far, the data show no deviation from Einstein's predictions, suggesting that if spacetime has an underlying structure, its effects must be subtle. Similarly, astronomers studied interference patterns from distant quasars. If spacetime fluctuated significantly at very small scales, the tiny distortions would accumulate as light traveled billions of years, creating a slight blur in the images. Observations with the Hubble Space Telescope and JWST show that quasar light remains sharp, even after crossing immense distances. This result does not rule out quantum structure, but indicates that any irregularities must occur on scales smaller than what these methods can detect. One of the most informative sources of insight comes from gravitational waves. Since 2015, detectors have recorded dozens of mergers involving neutron stars and black holes. These events compress spacetime intensely. The signals carry information about how spacetime behaves under extreme curvature. The waveforms match Einstein's equations closely, even in the final milliseconds before collision. Yet the detectors cannot probe the moment when two horizons fuse. That region lies below the threshold where classical relativity applies. Many researchers hope that future instruments, such as the space-based LISA interferometer planned by ESA and NASA, will measure gravitational waves from supermassive black hole mergers with far greater sensitivity. These observations may reveal subtle deviations hinting at quantum features. Historically, breakthroughs in understanding small-scale physics came from unexpected directions. In the early 20th century, Planck discovered quantization by analyzing blackbody radiation. Rutherford and Bohr uncovered atomic structure by observing spectral lines. In the 1960s, experimental work with particle beams revealed quarks. It is possible that hints about quantum spacetime will also emerge from observations rather than direct experiments. JWST, for instance, continues to detect galaxies that formed earlier than expected. Their rapid growth might reveal clues about how gravity behaved in the young universe. Another promising line comes from the study of high-energy particle collisions. Although current colliders cannot reach the Planck scale, theories suggest that quantum gravitational effects might appear indirectly through small deviations in scattering processes. So far, the data match the standard model with remarkable precision. However, the absence of anomalies can be informative. It narrows the parameter space of viable quantum gravity theories and guides researchers toward models consistent with both microscopic and cosmic observations. Singularities remain one of the clearest indicators that classical spacetime cannot be fundamental. In relativity, singularities form when mass compresses to a point where curvature diverges. Quantum theories, however, forbid the idea of infinite density. Many loop-based models predict that, instead of collapsing into a singularity, matter undergoes a bounce, reaching a minimum size before expanding again. Some string-based scenarios propose that singularities are replaced by extended regions where geometry becomes non-classical. NASA's studies of black hole accretion disks using instruments such as NISA provide additional information about regions near event horizons. These observations probe strong gravity environments where quantum effects may influence particle behavior. While current data align with relativity, they also reveal heating, magnetic turbulence, and rapid variability that require sophisticated models incorporating both quantum and gravitational physics. The possibility that space-time breaks into discrete units challenges one of the most deeply rooted assumptions in physics. For centuries, scientists assumed that space and time were continuous. Quantum mechanics already taught that energy and momentum come in discrete amounts. If geometry is also quantized, it would unify small-scale and large-scale phenomena under a single principle. Such unification would profoundly shape how we understand everything, from particle interactions to cosmic evolution. There is a story often told among researchers studying quantum gravity. In the 1980s, a group of theorists examined how different models behaved under extreme curvature. They discovered that even when starting from different assumptions, many models predicted that measurable quantities, such as area and volume, could not shrink indefinitely. This convergence convinced many physicists that discreteness might be a common feature of any successful quantum gravity framework. The mathematical tools needed to explore these ideas continued to develop. Numerical relativity simulates spacetime under extreme conditions. Lattice-based techniques approximate discrete geometries. High-precision astrophysical measurements refine constraints on possible models. Each step narrows the gap between theory and observation. Carl Sagan once remarked that science is a way of interrogating nature without forcing it to answer prematurely. As researchers explore the Planck frontier, they remain guided by that principle. Their models must match what JWST sees in early galaxies, what LIGO detects from mergers, what ESA's Gaia measures in stellar motions, and what particle colliders observe in small-scale interactions. A theory of quantum spacetime must be consistent with all these phenomena. Only then can it replace the smooth geometry of relativity at extremely small distances. As the Planck scale continues to reveal its significance, the next steps lead into an even deeper challenge, steering us toward Part 5, where black holes expose one of the greatest puzzles in modern physics and force researchers to reconsider how information behaves under extreme gravitational collapse. Do black holes destroy information, or do they expose the limits of our theories? A black hole becomes profoundly unsettling the moment we ask what happens to the information carried by anything that falls inside. Classical gravity predicts a silent one-way boundary where matter disappears forever, yet quantum physics insists that information can never be erased. When these two foundations of modern science confront one another, a deep inconsistency forms at the center of our understanding. This tension did not begin as an abstract puzzle. It emerged, gradually built from decades of observation theory and technological progress. In the early 1970s, researchers studying X-ray emissions from compact stellar remnants found objects so massive and dense that only black holes could explain their behavior. NASA's Uhuru satellite, the first orbiting X-ray observatory, detected intense bursts from Cygnus X1. Later, ESA's XMM Newton and NASA's Chandra X-ray Observatory sharpened the view, revealing hot accretion disks swirling just outside event horizons. These observations confirmed the predictions of general relativity with striking accuracy. According to Einstein's equations, a black hole is defined entirely by its mass, its electric charge, and its angular momentum. Any other characteristic of the material that fell in is smoothed away. This idea became known as the no-hair theorem. John Wheeler famously summarized it by saying, "Black holes have no hair." Wheeler's phrase meant that black holes erase all details except for these three properties. This description aligns well with observations. When astronomers used radio interferometry to image the shadow of the black hole in galaxy M87 in 2019, the ring-shaped structure matched the predicted geometry of a smooth event horizon. NASA, the National Science Foundation, and institutions worldwide contributed to the data that produced this image. It offered a remarkable confirmation of relativity's large-scale predictions. But while relativity describes the exterior of a black hole beautifully, questions about the interior run headfirst into quantum principles. According to quantum mechanics, information encoded in the state of any particle cannot be lost. Even if a system changes form, the underlying information must remain recoverable. This rule is as foundational to quantum physics as the curvature of spacetime is to relativity. The conflict deepened in 1974 when Stephen Hawking applied quantum field theory to curved spacetime. By considering how particle pairs form near the event horizon due to quantum fluctuations, Hawking discovered that black holes are not entirely black. They emit radiation. This emission causes the black hole to lose mass, gradually evaporating over immense timescales. A black hole with the mass of the Sun would take roughly 10, raised to the 67 years to evaporate. That conclusion stunned physicists. It implied that a black hole is a quantum object, not merely a geometric structure. Yet Hawking's calculation seemed to indicate that when the black hole finishes evaporating, the information about what fell inside disappears entirely. This violation of quantum rules became known as the black hole information paradox. Hawking remarked decades later that the paradox represented a fundamental conflict between quantum mechanics and general relativity. Observational progress made the paradox harder to ignore. As gravitational wave detectors recorded dozens of black hole mergers, the signals revealed that black holes evolve in ways consistent with relativity's clean structure. Their final ringdowns, measured with millisecond precision, matched theoretical waveforms calculated from Einstein's equations. But if black holes behave so classically on the outside, how does the quantum information carried by particles survive on the inside? Attempts to solve the paradox proliferated. Some theorists suggested that information might escape encoded in subtle correlations within Hawking radiation. Others argued that the event horizon might store information on its surface. A third camp explored the possibility that space near the horizon is not smooth at all, but contains complex structures created by quantum effects. Each proposal attempts to reconcile two frameworks that were never built to operate together. The difficulty also involves the meaning of an event horizon. In relativity, an event horizon is a boundary from which nothing can return. It is not a solid surface, but a geometric feature that marks the point of no escape. However, when quantum rules are added, the horizon becomes an active region where fluctuations can create particle pairs. NASA's NICER instrument, mounted on the International Space Station, studies X-ray pulses from neutron stars, offering indirect insight into matter approaching extreme gravitational fields. These measurements help refine models of spacetime near horizons. The no-hair theorem remains one of the most striking aspects of classical black hole physics. Wheeler's original statement was based on the idea that all details, except mass, charge, and spin, dissipate. But if black holes leave no trace of the material that formed them, and if they evaporate through Hawking radiation with no memory of what entered, then information seems truly lost. This conclusion contradicts quantum theory. The mismatch represents more than a complication. It challenges the consistency of both frameworks. Some researchers study this tension through the lens of quantum information science. They examine how entanglement behaves near event horizons. Hawking radiation appears thermal, which suggests randomness. Yet quantum theory requires that complete randomness must arise from an underlying structure. This line of inquiry has led to ideas such as black hole complementarity, which proposes that information is both reflected at the horizon and passes inside depending on the observer's perspective. Another influential idea involves the holographic principle. In the 1990s, work on string theory suggested that all information inside a region of space may be representable on its boundary. This principle gained strong support from calculations in models involving anti-de Sitter geometry. While our universe is not exactly described by that geometry, the success of these models revealed that information might never truly be lost because the horizon can encode everything. ESA's Gaia mission, while primarily designed to map stellar positions, has provided essential data on the motion of stars orbiting black holes in binary systems. These measurements help determine how matter behaves before crossing horizons. They also help identify whether any unexpected features appear near the threshold of no return. So far, the data align with relativity, offering no deviations that would point to a resolution of the information paradox. The Event Horizon Telescope continues to refine its imaging techniques. As new arrays come online, future images may capture details of magnetic structures and plasma dynamics that test the limits of classical models. These observations cannot look inside event horizons, but they can constrain the physics just outside where quantum and gravitational effects may interact. The most intense efforts to resolve the paradox involve studying what happens to information carried by quantum fields near the horizon. One widely discussed approach argues that information becomes encoded in correlations between outgoing radiation and the remaining black hole. This correlation strengthens as evaporation progresses. If true Hawking radiation would not be purely thermal, but subtly structured. Experiments cannot detect such fine patterns today, but theoretical calculations examine whether they could exist without violating relativity. More speculative ideas question whether horizons are smooth at all. Some models propose that quantum effects create energetic regions just outside the horizon. These structures, often nicknamed firewalls, would prevent information from being lost, but would contradict relativity's predictions. Because no observation has revealed such features, many physicists continue to doubt the need for them. Another direction explores whether black holes avoid forming singularities. If the interior avoids collapsing into a point of infinite density, then information might survive in a region where geometry remains finite. Loop-based models often produce such results. They suggest that collapsing matter reaches a minimum density before expanding again. Whether such an expansion could influence Hawking radiation remains an open question. Despite decades of work, no final resolution exists. Yet progress continues, measured by increasingly precise observations and more refined calculations. Gravitational wave detectors are becoming more sensitive. X-ray observatories measure emissions near horizons with growing accuracy. JWST probes early cosmic structures that may show effects from primordial black holes. Each piece of data narrows the range of possible answers. Stephen Hawking once described the paradox with the words, "Information loss would force us to give up quantum mechanics." The reverse is equally true. Preserving information might require modifying relativity. Between these extremes lies the possibility that a deeper theory will emerge, one that contains both classical geometry and quantum rules as approximations. As these competing ideas continue to evolve, the next layer of mystery comes into sharper focus, carrying us toward Part 6, where space-time near the event horizon becomes a testing ground for the most extreme collision between curvature and quantum fluctuations ever discovered. What really happens at the event horizon when quantum fluctuations meet curved space-time? The event horizon becomes deeply puzzling the moment we examine it through both quantum physics and general relativity at the same time. Relativity predicts a calm boundary shaped only by mass and spin, while quantum physics predicts restless fluctuations that never settle. When these two descriptions overlap, the horizon transforms into one of the most contested regions in modern science. To appreciate how this puzzle arose, we begin with the classical picture. For decades after Einstein introduced general relativity in the 1910s, physicists treated the event horizon as a geometric surface with no physical substance. It marked a boundary, nothing more. Light that approached too closely could not escape, but the horizon itself exerted no special force. This interpretation aligned remarkably well with observations. When NASA's Chandra X-ray Observatory and ESA's XMM Newton studied accretion disks circling black holes, they found that particles could orbit stably just outside the horizon before plunging inward. These observations matched the predictions of smooth, continuous space-time curvature. However, the quantum description of empty space is never empty. In quantum field theory, fields fluctuate constantly. Even in a vacuum, particle-antiparticle pairs appear briefly before annihilating. When Stephen Hawking analyzed these fluctuations near the horizon in 1974, he discovered that the curved space-time modified the behavior of these virtual pairs. One particle could fall inward, while its partner escaped outward, making the black hole lose mass over time. This emission later became known as Hawking radiation. The introduction of Hawking radiation shifted the discussion from classical geometry to quantum processes. Suddenly, the event horizon was no longer a passive boundary. It became a stage where quantum fluctuations interacted with extreme curvature. The horizon now carried entropy, a measure of how many microscopic configurations it could have. Bekenstein and Hawking showed that this entropy increases with the area of the horizon. Instead of being a simple geometric surface, the horizon held deep information about the black hole's internal microstates. This insight raised a profound difficulty. If the horizon has entropy, then whatever falls into the black hole must somehow influence that entropy. But the no-hair theorem states that black holes can be described entirely by mass charge and spin. The tension between these ideas became one of the central issues in black hole physics. Observations added further complexity. The Event Horizon Telescope's image of the M87 black hole revealed a bright ring consistent with emission from matter heated near the horizon. The ring's structure and size matched predictions from general relativity, confirming again that relativity gives an accurate, large-scale description of the horizon's geometry. But the image could not reveal quantum fluctuations. It showed only the macroscopic structure. To explore the quantum layer, physicists turned to theory. They studied how virtual particle pairs behave in curved spacetime. In flat space, quantum fluctuations appear randomly everywhere. Near a horizon, the curvature of spacetime stretches these fluctuations. A particle may be drawn outward, while its partner is pulled inward. The escaping particle contributes to Hawking radiation. The trapped partner carries negative energy relative to the black hole. When added over long timescales, this negative energy causes the black hole to evaporate. This description works well mathematically, but it creates a paradox. Hawking radiation appears thermal, meaning it carries no memory of what fell into the black hole. If the black hole evaporates completely, the information about the infalling matter seems irretrievably lost. But quantum mechanics does not allow information to vanish. This contradiction became known as the information paradox. The paradox grew even sharper when researchers examined entanglement at the horizon. In quantum mechanics, particles can share correlations, even when separated. Hawking radiation requires that the outgoing particle remain entangled with its partner inside. But if the black hole evaporates, the interior disappears. How can entanglement survive a conflict forms? Either quantum mechanics fails, or the classical picture of the horizon fails. One proposed solution is that information does not fall inside at all, but becomes encoded on the horizon's surface. This idea is related to the holographic principle. In the 1990s, theoretical work showed that certain gravitational systems could be described by a theory that exists only on a boundary. Although these models are not exact replicas of our universe, they revealed a powerful idea. It suggested that the horizon might store information in subtle patterns. Some calculations suggest that quantum effects create a highly energetic region at the horizon. This scenario is often described as a firewall. In this view, the horizon is not smooth, but violently active, preventing any infalling observer from passing through unharmed. The firewall proposal preserves information, but contradicts general relativity's prediction that an observer crossing the horizon feels nothing special. The debate grew more intense as researchers explored the physical consequences. For example, if a firewall existed, gravitational wave signals from black hole mergers might contain tiny reflections or echoes. Teams examining LIGO and Virgo data looked for such effects. So far, observations remain consistent with smooth horizons, although the sensitivity may not yet be sufficient to detect subtle deviations. A different line of research involves studying the entropy of horizons. The Bekenstein-Hawking formula shows that entropy increases with area, not volume. This suggests that the microscopic degrees of freedom associated with a black hole behave more like surface states than bulk states. If information is stored on the horizon, then Hawking radiation might carry that information out slowly over time. Some theoretical work supports this possibility, showing that correlations could arise between early and late radiation in a way that restores unitarity. Another perspective comes from studying the near-horizon geometry. In relativity, strong redshift effects occur close to the horizon. Light emitted just above the surface becomes stretched to lower energies when observed far away. This stretching would influence the behavior of virtual particles. Calculations show that quantum fluctuations intensify near the horizon because the gravitational field becomes extremely strong. Some researchers even argue that these fluctuations could imprint subtle patterns onto Hawking radiation. NASA's NICA instrument provides high-resolution X-ray timing measurements from neutron stars. These stars sit just above the threshold of collapse. Their extreme gravity makes them valuable laboratories for understanding strong curvature environments. NICA's data allows scientists to measure how gravity bends light near compact objects. While these observations do not probe the event horizon directly, they constrain models of how matter behaves just shy of collapse, contributing to our understanding of near-horizon physics. ESA's Gaia mission, designed to map stellar motions across the galaxy, has also refined measurements of stars orbiting black holes. Precise tracking reveals how space-time curvature influences motion. These results provide indirect evidence for the classical picture of the horizon, but offer no clues about what quantum features might lie beneath. Still, the consistency with relativity sets boundaries on how radical new models can be. The interplay between quantum fluctuations and curved geometry is also studied using numerical simulations. Computational physicists model how fields evolve as they approach horizons. These simulations show that small differences in initial conditions can produce large effects due to the extreme curvature. They help illustrate why the horizon is such a sensitive region for testing the limits of general relativity and quantum mechanics. Some researchers focus on how information might be recovered from Hawking radiation. They construct mathematical models showing that radiation, although thermal in appearance, could carry subtle imprints of the black hole's internal state. Detecting these imprints would require sensitivity far beyond current instruments, but their theoretical existence provides a potential resolution to the paradox. Others explore whether the horizon might not exist as a sharply defined surface at all. Some models suggest that quantum gravitational effects cause the horizon to fluctuate, blurring its location. If true, the traditional picture of a smooth boundary may give way to a dynamic region shaped by both curvature and quantum uncertainty. This convergence of ideas illustrates a central truth. The event horizon is the boundary where our best theories meet their limits. It is the surface where geometry and quantum rules collide, revealing the incomplete nature of both frameworks. Whether the horizon remains smooth, hides complex quantum structure, or contains energetic barriers, it represents one of the most challenging frontiers in physics. Stephen Hawking once remarked, "The universe may behave in unexpected ways. The event horizon embodies that message." It shows how a surface defined by geometry becomes a crucible for quantum effects, and how observations guide theory toward a deeper understanding. As the horizon continues to test the limits of our models, attention naturally settles on gravity itself. A place where certainty begins to thin, and where even the idea of a particle description starts to feel incomplete. This is where the next step unfolds. Part Sept. Is gravity a particle called the graviton, or something deeper than a force? Gravity becomes far more mysterious the moment we ask whether it behaves like the other fundamental interactions. Quantum field theory predicts that every force must arise from particles, yet when physicists attempt to assign gravity a particle of its own, the mathematics strains and refuses to settle. Is less than #0. 5# is greater than. This difficulty signals that gravity may follow rules unlike any other known interaction in nature. The idea of the graviton began with a simple analogy. Photons carry the electromagnetic force, gluons carry the strong force, and the weak force relies on W and Z particles. These carriers arise naturally from quantum field theory, where interactions occur through the exchange of quanta. If gravity fits this structure, then it should also have a carrier. Calculations show that such a carrier must be massless and must possess 2 units of intrinsic spin. But while this description matches the symmetry of Einstein's equations, constructing a fully consistent theory around it remains extremely difficult. The earliest attempts to quantize gravity followed the same guidelines that succeeded for electromagnetism and the nuclear forces. The gravitational field was treated as a small fluctuation on top of a fixed background spacetime. These fluctuations were quantized, allowing calculations of exchange processes similar to how photons mediate forces between electrons. But this approach quickly encountered divergences. Every correction term produced new infinities that renormalization techniques could not control. History shows why these problems mattered. In the 1940s and 1950s, quantum electrodynamics faced similar infinities. Yet precise experiments, including those by Lamb, Cush, and Foley, confirmed that the renormalized theory made accurate predictions. That success inspired physicists to expect gravity might follow the same path. But when the divergences in quantum gravity proved too severe, researchers realized they were confronting something fundamentally different. Observations across the cosmos added to the puzzle. Missions operated by NASA, ESA, and international partners confirmed that gravity behaves exactly as Einstein described on large scales. Gaia mapped stellar motions with micro-arcsecond precision, measuring how curvature influences trajectories across thousands of light-years. The Event Horizon Telescope captured the shadow of the black hole in M87, aligning remarkably with relativistic predictions. LIGO and Virgo measured gravitational waves with a clarity that matched the theory of curved spacetime, collapsing into simpler configurations. These measurements reinforced the idea that gravity behaves as geometry, not as a particle-mediated interaction. Yet quantum physics insists that nothing fundamental should lack a quantum counterpart. Even fields that appear classical at large scales have underlying quantum descriptions. So researchers looked for indirect evidence of gravitons. One approach studied the cosmic microwave background. Quantum fluctuations in the early universe should have produced faint gravitational waves that left patterns in the polarization of the background radiation. Experiments such as BICEP 2, Planck, and other ground-based observatories searched for these patterns. So far, the data reveal no definitive signs of primordial gravitational waves. The search continues, but the absence of detection highlights how difficult it is to find quantum signatures of gravity. Another approach examined high-energy cosmic rays. If gravitons existed as particle exchanges, extremely energetic collisions in space might reveal unexpected scattering behavior. Observatories designed to detect cosmic rays have not found these anomalies. The lack of evidence for graviton interactions at accessible energies suggests that gravity does not behave like the other forces within the range of current experiments. At this point, a deeper idea entered the discussion. Perhaps gravity is not a force in the traditional sense. Instead, it may be an emergent phenomenon that arises from more fundamental components of the universe. This notion is similar to how temperature emerges from the motion of molecules. Temperature is real and measurable, yet it does not exist as a particle. It arises from collective behavior. Some physicists propose that space-time itself may emerge from underlying quantum processes. Others suggest that gravity results from statistical tendencies, where geometry reflects the behavior of microscopic degrees of freedom. Studies of black hole thermodynamics contributed significantly to these ideas. Bekenstein and Hawking showed that black holes possess entropy proportional to their horizon area. This discovery implies that space-time may contain discrete building blocks that behave collectively to create curvature. The concept of emergent gravity has been explored through various models. Some rely on entanglement patterns, where the structure of space-time reflects the entanglement between quantum states. Others use analogies from condensed matter physics. For example, certain materials exhibit behaviors at large scales that cannot be traced to a single particle type but emerge from collective dynamics. This analogy encourages the possibility that gravity could arise from deeper interactions we do not yet understand. Meanwhile, effective field theories provide another perspective. Instead of demanding that gravity behave like a particle-mediated force at all scales, this approach accepts that gravity behaves classically at large distances and only requires a quantum description at energies far below the Planck scale. In this framework, quantum corrections to gravity exist, but are too small to observe with current instruments. This approach remains consistent with all known measurements, from lunar laser ranging to timing variations in pulsar binaries. Through each of these efforts, a central tension remains. If the graviton exists, it must appear as a massless spin-2 particle whose interactions reproduce Einstein's equations at large scales. But constructing such a theory without encountering uncontrolled divergences has proven challenging for decades. This challenge hints that gravity might not originate from particle exchange. It may originate from something deeper. This possibility becomes clearer when studying gravitational waves. LIGO and Virgo have measured waves from dozens of black hole and neutron star mergers. These waves travel at the speed of light, consistent with a massless carrier. But the waves also represent distortions of space-time itself. Unlike photons which propagate through space-time, gravitational waves are oscillations of the space-time fabric. This dual nature complicates the graviton picture. While the waves might correspond to large-scale bundled excitations of a quantum field, the analogy is not perfect. Another strand of evidence comes from studies of the universe's expansion. ESA's Euclid mission and NASA's upcoming Roman Space Telescope will measure how galaxies cluster and how dark energy influences cosmic structure. If gravity deviates from Einstein's predictions at large scales, the data may reveal it. Some emergent gravity frameworks predict subtle differences in how galaxies move. These missions could provide essential insight into whether gravity is truly fundamental or emergent. The search for gravitons continues at particle colliders as well. Although the energies required to produce gravitons directly far exceed current capabilities, some theories predict that gravitons could escape into hidden dimensions. If such events occur, energy would appear to vanish from collision products. Experiments at the Large Hadron Collider have searched for this effect but have not observed it. The results constrain many models, leaving fewer possibilities. Carl Sagan often reminded audiences that science advances by confronting its boundaries. The graviton problem represents one of those boundaries. We lack the evidence needed to decide whether gravity fits into the quantum picture or stands apart. What keeps the search alive is the possibility that gravity hints at a deeper layer of reality, one that spans the microscopic and cosmic scales. As current missions refine our measurements of cosmic structure and future detectors listen for fainter gravitational waves, the puzzle may gradually come into view. Whether gravity emerges from unseen building blocks or originates from a spin-2 quantum field, its nature will shape our understanding of the universe's foundations. As this search continues to widen, another difficulty becomes impossible to ignore. When Einstein's equations are pushed into a quantum framework, the mathematics itself begins to break down, producing instabilities and infinities that signal a deeper problem with how spacetime is being described. Part Wit. Why do our best attempts to quantize Einstein's equations explode into infinities? The moment physicists try to quantize Einstein's equations, the mathematics rises uncontrollably, as if the very structure of spacetime rejects being treated like an ordinary quantum field. Each attempt to apply the familiar rules of quantum theory produces new infinities layer after layer until the equations lose all predictive meaning. This problem reaches back to the late 1960s, when researchers first attempted to place general relativity inside the same quantum framework that successfully described electromagnetism and the nuclear forces. Those forces behaved well. Their quantum theories allowed infinities to be cancelled by a method that adjusted masses and charges in a controlled way. But Einstein's equations resisted the same treatment. The difficulty begins with the fact that gravity is inherently nonlinear. In relativity, spacetime curves in response to energy, but that curvature itself contributes additional energy, which causes further curvature. This self-interaction is built directly into the equations. When physicists expand the geometry into a background plus small vibrations, and then quantize those vibrations, the nonlinear nature of the equations makes every correction generate new terms. These terms feed into one another, producing divergences that renormalization cannot tame. Attempts to manage these divergences reveal the uniqueness of gravity. In quantum electrodynamics, loop corrections alter the behavior of electrons and photons in consistent patterns. The corrections are finite once renormalization is applied. Precise experiments, such as the measurements of the electron's magnetic moment, confirm the success of that approach. Gravity does not offer such stability. Each loop correction introduces additional infinities that require additional counterterms. Adding counterterms does not rescue the theory, but instead multiplies its parameters, eliminating its predictive power. Observations across the universe underscore why this matters. NASA's Hubble Space Telescope, ESA's Gaia mission, and the Event Horizon Telescope all confirm that relativity describes large-scale behavior with remarkable accuracy. Spacetime curves exactly as Einstein predicted, but these observations cannot address the quantum structure of spacetime. They show only the macroscopic behavior, leaving the microscopic realm open. The first systematic attempts to build a quantum theory of gravity used perturbation theory, the same method that works so well for the electromagnetic force. The idea was to take the spacetime metric, split it into a smooth background plus small fluctuations and quantize the fluctuations. But the background itself has no fixed identity in relativity. Unlike electromagnetism, which exists on top of spacetime, gravity is spacetime, Treating spacetime as if it sat on another structure undermines the theory's foundations. This problem was recognized early. In the 1970s, theoretical physicist Bryce DeWitt worked extensively on the canonical quantization of gravity. Alongside John Wheeler, he developed an equation that attempted to describe quantum states of spacetime. But the result removed the concept of time from the equation entirely. The Wheeler-DeWitt equation became a striking example of how quantum tools distort the familiar structure of relativity when applied directly. Even today, it remains a cornerstone of discussion but not a fully operational theory. Experimental work added further tension. As particle accelerators reached higher energies, physicists hoped to find hints of quantum gravitational behavior. Yet collisions at CERN, even those probing distances far smaller than a proton, revealed no signature of graviton interactions. The standard model of particle physics remained robust, while gravity remained outside the framework. Studies of black hole thermodynamics strengthened the need for a quantum description. The Bekenstein-Hawking formula relates the entropy of a black hole to its horizon area. This discovery strongly suggested that spacetime contains microscopic degrees of freedom. Entropy typically reflects the number of internal configurations of a system. If a horizon has entropy, then geometry must have an underlying structure. This realization created pressure to develop a quantum description of spacetime. Yet the direct quantization of Einstein's equations continued to produce infinities that overwhelmed the theory. Attempts to circumvent this difficulty led researchers toward effective field theory. In this approach, gravity is treated as a classical background with small quantum corrections. The corrections behave well at low energies. Lunar laser, ranging GPS timing variations, and pulsar observations confirm this semi-quantum description. But as energy increases toward the Planck scale, the effective theory breaks down. It offers no insight into the fundamental structure of spacetime. Some of the most illuminating evidence comes from cosmology. ESA's Planck satellite mapped the cosmic microwave background with extraordinary precision. The tiny fluctuations in temperature reflect quantum fluctuations stretched by cosmic inflation. These fluctuations seeded the formation of galaxies. Their structure aligns with models of early universe physics that require some form of quantum gravity. Yet the data do not reveal what that quantum gravity is. They show the effects, but not the underlying mechanism. Gravitational wave observations have added new depth. When LIGO detected the merger of two black holes in 2015, the signal matched Einstein's predictions with outstanding precision. These waves represent oscillations of spacetime itself, suggesting that if a quantum description exists, it must reproduce these patterns at large scales. But the very success of relativity makes the quantum problem harder, not easier. The theory works so well that any quantum extension must preserve its predictions precisely, while also resolving its divergences. Historical attempts to fix these issues reveal consistent patterns. In the 1970s, physicists Arndt Hooft and Veltman discovered that if gravity were slightly different, if it involved a special symmetry, then some divergences might cancel. But with the known structure of the universe, these cancellations do not occur. Later work on supergravity attempted to add new fields that might stabilize the theory. Although the mathematics became more elegant, divergences still appeared at higher loop orders. The failure of perturbative methods encouraged new directions. Non-perturbative approaches attempt to rebuild gravity from scratch without relying on small fluctuations. One such method is loop quantum gravity, which quantizes geometry directly. In this picture, area and volume come in discrete amounts. Another approach uses causal dynamical triangulations, where spacetime arises from the accumulation of tiny geometric building blocks. These models avoid some infinities, but none has yet matched all known observations. Another major direction comes from string theory. By replacing point-like particles with tiny vibrating strings, the theory naturally avoids the infinities produced when point particles interact. String theory also predicts additional dimensions which may influence gravity at small scales. The theory remains one of the most extensively studied frameworks for quantum gravity, but it lacks direct observational confirmation. While theoretical models evolve, observational programs continue to tighten constraints. JWST probes early galaxies whose structures may hold clues about how gravity behaved under conditions close to the Planck regime. ESA's LISA mission, scheduled for the 2030s, will detect lower-frequency gravitational waves from supermassive black hole mergers. These signals may reveal whether classical relativity holds perfectly or whether faint quantum corrections alter the waveforms. The persistence of divergences in quantized relativity suggests that the gravitational field may not be a fundamental variable. Some theories propose using different mathematical objects to describe spacetime, such as connections instead of metrics. Others explore whether spacetime itself emerges from entanglement patterns, making geometry a secondary phenomenon rather than a primary one. Carl Sagan once reminded audiences that science advances through humility, noting that we are forever students of a universe far older and more complicated than our brief existence. The search for a quantum theory of gravity reflects that humility. Each attempt reveals a boundary, showing that our familiar tools cannot extend indefinitely. As researchers continue to explore alternatives, one insight becomes increasingly clear. The infinities produced by perturbative quantization are not simply technical problems. They may signal that new variables, new principles, or new structures lie beneath the surface of spacetime. As the mathematical difficulties make it clear that a deeper framework is required, multiple approaches come into view. Loop quantum gravity, string theory, and holography each attempt to describe that underlying layer of reality, suggesting a structure of the universe that neither relativity nor quantum mechanics can fully capture on their own. Part 9. Are loop quantum gravity, string theory, and holography competing universes or different shadows of one deeper reality? A deeper fracture in physics appears the moment scientists compare the three most ambitious attempts to describe spacetime at its smallest scales is less than #0. 5 is greater than. Each theory captures a different aspect of gravity's quantum structure, yet none of them gives a complete picture, as if nature were showing us several shadows of a framework we cannot yet see directly. The first attempt, loop quantum gravity, emerged in the 1980s. Its central idea is that spacetime itself is built from discrete units. Instead of a smooth fabric, the geometry becomes a web of quantized links. In this picture, the area of a surface and the volume of a region can take only specific values. They do not shrink continuously, but jump between fixed steps, much like energy levels inside an atom. This approach grew from an effort to preserve Einstein's geometric interpretation of gravity, while adding quantum rules directly to the fabric of spacetime. Researchers constructing this framework analyzed how these quantized loops form networks. These networks evolve in time, creating a dynamic structure where geometry is not something space has, but something space is made of. Early supporters found encouragement when the theory naturally removed singularities. In certain versions, the Big Bang becomes a bounce. Collapse inside a black hole avoids infinite curvature, because distances cannot shrink beyond the smallest quantum unit. Observational evidence does not confirm loop-based models yet, but data from ESA's Planck satellite and NASA's cosmic microwave background experiments remain consistent with the possibility of discrete geometry at the earliest moments of the universe. The fluctuations imprinted on the cosmic microwave background reflect quantum processes stretched across cosmic expansion. They do not reveal the underlying structure, but they leave room for a geometry built from quanta. A very different approach emerged from string theory. Instead of quantizing geometry itself, string theory proposes that the most fundamental objects are vibrating strings. Their vibrations determine particle properties. A particle with different mass or spin is simply a string vibrating in a different mode. This picture unifies the forces by embedding them within a single structure. Gravity arises naturally from one of the vibrational modes, avoiding the divergences that plague attempts to quantize point particles. String theory predicts additional dimensions. These dimensions are compact and hidden, folded into shapes so small that experiments cannot detect them. This idea became mathematically compelling in the 1980s and 1990s, especially after researchers discovered that different versions of the theory may represent the same underlying framework. This discovery suggested that string theory might possess a depth far greater than originally expected. Hints of these additional dimensions occasionally surface in discussions of early universe cosmology. For example, certain inflation models inspired by string theory produce unique patterns in the cosmic microwave background. ESA's Planck mission looked for these signatures but found results consistent with simpler models. Still, the possibility remains open, especially as astronomers push deeper into space, with JWST detecting galaxies formed when the universe was only a few 100 million years old. These galaxies reveal structures that challenge existing models and could eventually help test ideas rooted in higher dimensional frameworks. The third major idea, the holographic principle, emerged from black hole thermodynamics. It began with the discovery that black holes possess entropy proportional to their surface area. This suggested that the information inside a region of space might be encoded on its boundary. The principle was later refined through theoretical work showing that certain gravitational systems can be described completely by a theory defined on a lower dimensional boundary. The most famous example involves anti-de Sitter spacetime and conformal field theories, often referred to as ADS, CFT. Although our universe does not have the structure of anti-de Sitter spacetime, the correspondence revealed that gravity may emerge from quantum correlations. Geometry might be a consequence, rather than a fundamental ingredient. NASA's research on quantum entanglement experiments aboard the International Space Station indirectly supports this direction by studying how entanglement behaves under different conditions. Though not directly connected to holography, these experiments refine our understanding of quantum correlations, which might be central to the structure of spacetime. These three frameworks appear to be competing, but each solves different pieces of the puzzle. Loop quantum gravity explains how geometry might become discrete. String theory explains how particles and forces could unify and avoid divergences. Holography explains how geometry itself might emerge from purely quantum information. Behind each of these theories lies a rich history of discovery and struggle. In the 1990s, researchers working on string theory attempted to calculate black hole entropy using strings and found that their results matched the Bekenstein-Hawking formula in specific cases. This connection between microscopic string behavior and gravitational entropy gave the theory newfound credibility. Around the same time loop, quantum gravity researchers discovered that their quantized area operators also reproduced black hole entropy values under certain conditions. Two theories built from different assumptions both produced the same physical quantity. This coincidence suggested that the deeper framework might contain elements of both. The holographic principle added further depth when studies revealed that spacetime geometry in certain models arises from entanglement patterns. These entanglement structures determine distances and curvature. If entanglement decreases in a region, the corresponding part of spacetime contracts. This idea suggested that gravity may not require gravitons as fundamental particles, but may instead emerge from more fundamental quantum interactions. Observations from gravitational wave detectors provide independent insight. When LIGO recorded the first merger of two black holes, the waveform showed astonishing precision consistent with classical gravity. Yet the final state emitted slightly less energy than earlier models predicted. The difference was small and not statistically significant, but it encouraged researchers to consider whether subtle quantum effects might exist just below the sensitivity threshold. Future instruments such as LISA could detect features that reveal whether gravity's behavior at strong curvature aligns more closely with one theoretical framework than another. Studies of dark energy and cosmic expansion also feed into the discussion. ESA's Euclid mission and NASA's Roman Space Telescope aim to map cosmic structures and determine whether gravity behaves differently at large scales. If deviations from Einstein's predictions appear, they could point toward a deeper framework that combines elements of emergent gravity with features of string theory or holography. Another important clue comes from condensed matter analogies. Certain materials exhibit emergent behaviors that do not resemble their underlying components. For example, collective oscillations of atoms can behave like particles with different masses and spins. These analogies demonstrate that particle-like behavior can arise from collective dynamics. They also show how geometry can appear in systems where geometry is not a fundamental ingredient. These ideas support the possibility that space-time geometry may emerge from deeper quantum structures. Each theory also faces significant challenges. Loop quantum gravity struggles to reproduce the classical picture of smooth space-time at large scales. String theory, while mathematically rich, has a vast landscape of possible solutions. Holographic models often rely on space-times that do not resemble our universe. The weaknesses are different, but none can be ignored. When researchers compare these theories, they often discover connections that hint at a deeper unity. For example, certain loop-based calculations resemble structures found in string-based models. Holographic descriptions often contain discrete elements, reminiscent of loop quantum gravity. These overlaps strengthen the idea that each theory might represent a different approximation of one underlying reality. Carl Sagan's words, "Somewhere something incredible is waiting to be known," express a sentiment that resonates strongly with physicists attempting to reconcile these frameworks. The universe reveals fragments of its structure through gravitational waves, cosmic background radiation, quantum field behavior, and black hole thermodynamics. Each observation narrows the range of possibilities, pulling theory closer to reality. As researchers examine how geometry can arise from quantum information, how strings vibrate within compact dimensions, and how spacetime itself may be built from discrete elements, a more unified picture begins to take shape. If quantum gravity is realized, its consequences extend beyond technical details, reshaping how time, causality, and the structure of reality are understood. Part this. What will change in our picture of reality if quantum gravity finally exists? Reality begins to shift the moment we imagine a universe where quantum gravity is no longer a distant dream but a working theory. The singularities at the centers of black holes dissolve. The first instant of the Big Bang takes on structure instead of infinity, and the very notions of time and causality reorganize into forms we have never fully seen before. To understand what this transformation means, we return to how our current theories behave. General relativity describes spacetime as a smooth surface that curves around mass and energy. Quantum mechanics describes matter and fields as discrete fluctuating quanta. These two pictures work flawlessly in their own domains, yet fail in the regions where the universe becomes most extreme. Black hole interiors, the earliest fractions of a second after cosmic expansion began, and the Planck-length boundary where geometry itself starts to shift. All of these environments reveal that something deeper must govern the structure of nature. When researchers examine data from NASA's Hubble Space Telescope, ESA's Gaia mission, and the Event Horizon Telescope, they found that relativity describes the universe with astonishing precision across astronomical scales. Gravity bends, starlight stretches time, and shapes galaxies, exactly as Einstein predicted. But the same decade of observations also revealed that quantum physics dominates small-scale phenomena with equal precision. Experiments in particle accelerators detect quantum interactions down to distances smaller than 1/1,000,000,000th of a meter. Both theories remain correct in their realms. Neither works where the other is required. Quantum gravity aims to bridge this divide. If successful, it would provide a framework that contains both relativity and quantum mechanics as limiting cases. This would allow scientists to describe black hole evaporation without losing information, to explain the earliest moments of cosmic expansion without singularities, and understand how space-time behaves when compressed to the smallest conceivable scales. One of the most striking consequences involves time. In relativity, time is intertwined with space, forming a four-dimensional geometry. That geometry tells clocks how to tick. In quantum mechanics, time enters as an external parameter, not a fluctuating object. A quantum theory of gravity would need to reconcile these roles. Some models suggest that time may not be fundamental, but may emerge from deeper processes, similar to how temperature emerges from molecular motion. Evidence for this possibility appears indirectly in the behavior of extreme gravitational environments. For example, when NASA's NICA instrument studied X-ray emissions from neutron stars, it recorded how space-time curvature affects the timing of pulses. These measurements reveal subtle distortions caused by intense gravity, linking the flow of time tightly to the shape of space. But quantum mechanics treats time differently. A theory uniting these descriptions may require a radical reinterpretation of what before and after truly mean. Singularities provide another window. In classical relativity, singularities arise inevitably when space-time curvature grows without bound. Inside a black hole or at the start of the universe, the equations predict infinite density and zero volume. Physics loses meaning. But quantum gravity frameworks such as loop-based models or string-based approaches often avoid singularities by giving space-time a discrete structure. Distances cannot shrink indefinitely. Geometry acquires quantum granularity. Instead of a singularity, collapse might reach a minimum size before transitioning into a new state. Observations from JWST highlight why resolving these issues matters. JWST sees galaxies forming earlier than expected, with structures that challenge standard cosmological models. If quantum gravity modifies early universe behavior, these early structures might hold records of physics beyond our current theories. Their unexpected brightness and rapid development may offer clues about how space-time evolved before the familiar expansion took shape. Gravitational wave observations also push the need for a unified theory. When LIGO recorded the waves from merging black holes, the signal matched Einstein's predictions until the final moment before formation of a single horizon. The instant after, however, remains hidden. That region lies beyond classical reach. A quantum theory of gravity could describe that transition, fully showing how space-time reorganizes as it absorbs the final fragments of matter and radiation. Even practical technologies would shift under quantum gravity. GPS satellites rely on relativity to correct the flow of time between Earth's surface and orbit. Those corrections ensure navigation remains accurate to within meters. A deeper theory could refine such timing, further improving technologies dependent on atomic clocks. If time behaves differently at extremely small scales, the effects might one day become detectable in precision timing networks. Cosmology, too, would undergo transformation. The Big Bang model currently describes the universe beginning from an incredibly dense state. A quantum theory of gravity could replace that beginning with a transition. A bounce, a phase change, or a shift from a prior state of geometry. ESA's Planck satellite already revealed the imprints of quantum fluctuations amplified during cosmic inflation. A fully developed quantum gravity theory would explain where those fluctuations originated. It would identify the processes shaping the earliest seeds of structure that later formed galaxies and clusters. Understanding causality would be equally transformative. In relativity, Events follow a clear order. Causes precede effects, determined by the structure of space-time. Quantum mechanics, however, permits situations where the distinction between cause and effect becomes blurred. Experiments have shown that quantum particles can behave as if events influence one another, without a fixed sequence. A quantum theory of gravity may unify these views by showing how causality emerges at large scales from underlying processes that do not require it. There is a story often recalled among physicists about the development of black hole thermodynamics in the 1970s. When Jacob Bekenstein first proposed that black holes have entropy, the idea seemed strange. Entropy measures microscopic information, yet classical black holes were featureless. But Hawking radiation, discovered shortly afterward, supported the idea. Entropy, indeed, related to horizon area, suggesting that space-time had microscopic degrees of freedom. That recognition became one of the clearest signals that quantum gravity must exist. The next decades produced further insights. Theories based on strings, loops, and holographic descriptions revealed surprising mathematical coincidences. In several cases, different models produced the same value for black hole entropy. This convergence suggested that distinct approaches might represent different slices of a deeper framework. The holographic principle in particular revealed that geometry might arise from quantum information. If true, space-time itself would not be fundamental but emergent. The implications stretch into every field of physics. If space-time emerges from quantum correlations, then gravity becomes a reflection of deeper rules that govern information flow. These rules would explain how mass curves geometry, why gravitational waves propagate as they do, and how singularities vanish when viewed through a quantum lens. Observations from LISA, once launched, could test these ideas by detecting gravitational waves from supermassive black hole mergers with precision far beyond current instruments. Carl Sagan once said that the universe is under no obligation to make sense to you. Kip Thorne echoed the same sentiment when describing the complexity of space-time. A successful quantum theory of gravity would reveal why nature behaves the way it does, showing how order emerges from the smallest components of the cosmos. It would not simplify reality, but illuminate the structure beneath it. Such a breakthrough would not only reshape textbooks, it would reshape what we consider possible. Time might not be a river, but a pattern. Space might not be a stage, but a product of deeper interactions. The beginning of the universe might not be a true beginning, but a transition. And black holes might not hide information, but process it. As this long journey through gravity, geometry, and quantum structure reaches its final step, the horizon of discovery stretches wider, reminding us how much remains to be learned. The mysteries that guided this exploration continue to unfold in data from NASA, ESA, JWST, and the instruments still to come. And as you settle into rest, may these ideas stay with you softly, forming a calm space in your thoughts. If this journey has brought you a small sense of calm before you close your eyes, I'm truly grateful that you stayed with me until the very end. A simple subscription or a gentle tap on like is a real source of encouragement, and it helps me continue creating these explorations for you. Is less than #0. 5# is greater than. And if you feel like sharing, I would love to know where you are listening from and at what time. Those small details help me better understand the people who are here with me. Wishing you a comfortable night and a deep, restful sleep.